Hi, everyone. Whoa, very weird echo. Okay, gotta get used to that. Thanks for coming to my talk. It is called Fast Inference, Furious Scaling. I hope you get the movie reference. I'm pretty proud of that title name, not AI generated. I came up with it myself. My name's Rafael, and that title is not just about the two tools, vLLM and KServe that I'll be talking about later today. But it's also meant to kind of capture the space of LLMs in general. There's new tools, new techniques, new announcements every day. And this can be very overwhelming for beginners who want to contribute to that space and specifically, the AI space and contribute to those types of projects. And so I kind of made this talk towards people who might have heard of vLLM or KServe, but don't really know what they do or where they fit in. And another thing is the idea that us developers usually don't have access to production environments unless our enterprise or organization have it to actually see what these tools are like in action. So that's sort of the spirit of this talk. And the way I'll do that is by giving a background on why serving LLMs is challenging in the first place, and then show how vLLM and KServe try to solve those problems. At the very end, I put them together in a bit of an absurd way by trying to run them on just my local laptop, and I'll give a bit of background on maybe why or what that actually looks like as well. So a bit about me. Like I said, I'm Rafael. I'm a software developer on the open technology team at IBM. I've been there for about 2 or 3 years, and most of my job is, aside from development, the ideas like presenting workshops and mentoring new contributors towards their first contribution, something I really enjoy doing. I also previously maintained a project called Model Mesh, which is a component of the KServe platform. Again, you'll learn about that later. And more recently, I began to contribute to vLLM as a project. And while Model Mesh and KServe were more in the kind of model serving space, vLLM was me delving more into, I guess, the inferencing side of things. And again, that kind of is why I made this talk the way it is, because I noticed it's a pretty, crazy, deep space. So to start, why is serving LLMs hard in the first place? So firstly, what does it actually mean to serve a model? Well, very simply, serving a model is just about making it available to users so that they can send inference requests and receive a response. Very straightforward. Like the idea that when we use some cloud-based services, like maybe you use a ChatGPT or a Gemini, those models have been made available to you to actually send the prompts and receive the responses. And usually there's multiple models hosted, right? You can kind of click between different models. These models are being served to you so that you can actually consume them, and usually that's via some kind of API endpoint. But of course, it's not actually that simple. A lot happens behind the scenes, right? When you actually click enter on your prompt, that prompt is getting broken down into tokens. The model processes those tokens in order to generate some kind of prediction, and then that response has to get decoded and sent back to you as output. And so just like any memory-intensive software program, large language models bring performance trade-offs, infrastructure constraints, and cost considerations. They cost a lot of money to run. And so in a bit more detail, why is it actually hard to serve large language models? Well, as we all know, they're huge. Just as an example, hosting the 70 billion parameter version of Llama 3 can use around 150 gigs of GPU memory. And relative to that, OpenAI's GPT-4, and this is like a rumored/estimated number, it's estimated to have some over 1.5 trillion parameters, even like way bigger, right? So simply put, hosting models at this scale actually requires having the hardware, the memory, and the infrastructure to actually run them. And most of us don't have that type of infrastructure sitting at our desks at home. Not only are LLMs huge, but they're also complex. An LLM is not just some black box function that just spits out text under the hood. The model is doing a lot of work to generate each token in the responses. And one of the first things it does is something called tokenization. Tokenization is that process of breaking down text into smaller units called tokens, and that visual kind of shows you kind of what that looks like. And these tokens could be words, parts of words, or even individual characters. And only after tokenizing does the model process the tokens to generate a response in the form of new tokens, and then ultimately convert those tokens back to the characters or text that you can actually read. And tokenization then kind of leads us to this next factor, which is just how much input can a model actually process at once. And this is what we refer to as context length. Some models can handle a few thousand tokens, others manage hundreds of thousands. As you can see, models like Granite 3, Llama 3, and GPT-4 Turbo, they support 128,000 token context lengths. But regardless of what that maximum is, this means that the longer your prompt or conversation gets, there's more computing that the model has to do. But why does that actually make it slower? And that's because of the way that models actually generate the responses. They generate responses one token at a time. And every single time that they produce a new token, that token is added back into the input, and then that whole sequence is processed again in order to predict the next token. So this is like a sort of loop over and over until that full response gets generated. And this is the idea of autoregressive models. The longer the output, the more expensive to compute, because each new token increases the amount of work needed for the next. And this is just a simple illustration of what that autoregressive generation looks like. My input here at the left is the dog. The model predicts the word is, and then the new input into the model will be the dog is. And then that model will now predict barking. And then this continues until it predicts some end of sequence token. So hopefully you can appreciate just how much a model is doing and looping through these calculations when you ask it to write an essay for you. So now that we know that LLMs are not just big and they're computationally complex as well, multiply all of that by all of the users sending requests at the same time. That's where scaling comes in and brings a whole new set of challenges. For example, when demand spikes, like any service, you need to make resources available quickly, or more resources available quickly. So you need to dynamically scale without dropping any of the requests that are coming in. And then somewhat unique to LLMs is the fact that you can't just send incoming requests to any available server, right? So if you're hosting multiple models and somebody's sending requests to one specific hosted model, and then traffic spikes, and so you need to maybe send some of those requests to some other replica of the model. You can't necessarily do that, because if that person was chatting with the model and maybe referring back to the idea of context length, there could be session context that gets lost. And that makes the idea of load balancing the requests a lot more complicated. Plus, spinning up new models isn't instant. They can take minutes, and we have to consider that too when it comes to actually scaling up to meet demand. So to wrap up this section, why is serving LLMs hard? LLMs are big, they use up a lot of resources, and that makes scaling them even more complicated. My hope is that with an appreciation for all of these hurdles, we can then now better understand how all of the tools out there actually fit in and try to tackle these things. And so that's where tools like vLLM come in. And so we'll start with vLLM, which focuses on making inference faster. vLLM is an open source inference engine, inference and serving engine that originated out of UC Berkeley by researchers there. And simply put, its main goal is to speed up the output of LLMs by optimizing the resources that it's using, like GPU memory. It's also a great example of a healthy open source project. It has over 1,000 unique contributors. It's very popular, I think like 50,000 GitHub stars, superficial stats, but very active community, and you can see if you go to the repository just how many PRs are open, how many issues. They do office hours weekly, and they're always very open to new contributions. But more importantly, how does vLLM actually do it? How does it make that inference faster? I'll quickly touch on 3 techniques that vLLM is using under the hood. The first of which is something called PagedAttention, which is an attention algorithm. The researchers, I'll mention that vLLM, the people who came up with vLLM, the researchers, they have a research paper on PagedAttention, and it's very much worth reading. They also introduce the vLLM project on top of that as well. But in that paper, they found that one of the biggest memory bottlenecks in LLM inferencing is something called the KV cache. And the KV cache is basically where the model stores the relationships between words that it has already seen, so that it doesn't have to recompute them every single time, right? It's like a cached memory of those relationships, right? More mathy than that, but that's kind of simply put. The team there discovered that traditional systems were actually wasting between 60 to 80% of memory the way that they were actually managing this cache. And so, inspired by the way that operating systems use virtual memory and the concept of paging, they applied that same technique to the KV cache. And so instead of treating that cache as just one big block, they essentially just break it down into smaller, flexible chunks, and that results in faster lookup and more efficient memory usage, less wasted memory space. And they found that this actually reduced memory waste to just 4% at the high end, right? It was like a near 0% wastage of memory. Another key technique used in vLLM is called continuous batching, where traditionally in static batching, you'll collect a bunch of requests that have come in, you process them all together, and then only when all of those requests have been handled, you start on the next batch. With continuous batching, the batch is handled more like on the fly, and it can grow and shrink dynamically as requests come in and finish. So instead of waiting for a whole new batch to start, meaning that your GPU resources are idle, waiting for that batch to finish, new requests that come in get added to the current batch that's being worked on, and this means that your GPU resources are actually constantly working. And this is specifically useful in these like high load scenarios where you might be handling hundreds and thousands of inference requests at once. And yet another piece of the puzzle, which is sort of like the way that vLLM actually helps with the features like PagedAttention, is its optimized CUDA kernels. CUDA is that low-level programming language used to speak directly to GPUs, and vLLM comes shipped with its custom code that is specifically optimized for some of those KV cache operations explained in that PagedAttention paper. And this helps with efficiency, using resources more effectively, which results overall in faster and cheaper performance. And now we kind of switch gears. Those are just some of the ways that vLLM makes the model itself run faster. But then when you're dealing with lots of users, or maybe you want to serve multiple models, you need a system that can actually scale up, do things like routing the traffic, and actually manage those models. And that's where a project like KServe fits in. KServe is an open source platform built on Kubernetes that takes care of things like deploying, scaling, and managing the models in production. It's basically like a one-stop shop trying to abstract all of the complexities of model serving infrastructure in general. And because it's built on Kubernetes, it's benefiting from all of the things that Kubernetes is good at, like fault tolerance and auto healing and all of the resilience and scaling features that it handles. So related to LLMs, what are some of the specific things that KServe helps with? Well, first, KServe manages autoscaling. I've sort of alluded to this, but the autoscaling is the idea of automatically creating more replicas of a model to manage the load when traffic increases, just like any service. When traffic drops, it also scales those replicas down in order to save resources and costs. So you might ask, what about the fact that models can take minutes to load up? What does that look like with autoscaling? Well, KServe has another feature called the local model cache. And this means that once a model is downloaded to a node, it can be stored locally and kept warmed up, ready to go basically reducing the startup time. And so when new replicas are needed, the model is ready to be loaded and served requests instantly. And finally, KServe also supports KV cache offloading through another project called LM Cache. I think there might have been a couple of talks maybe referring to this project elsewhere in the summit. But this basically lets parts of that KV cache that I mentioned, which holds those relationships between the words for the model to refer back to, because it gets so big, it can actually, parts of it can get moved off of the GPU into other storage or CPU, which ends up freeing up GPU memory for other things. And this helps with the idea of like the large context lengths that I mentioned before, right? Longer conversations where that KV cache can grow very large and the model has to work through all of those tokens. So, putting them together. We've covered some of the main pain points around inferencing and serving large language models. And you now know a bit about how vLLM makes that model run faster and how KServe helps with the operational side, like scaling and managing those models. And now I wanted to bring it back to what I mentioned at the very beginning of the talk, which is how beginners may want to actually learn about these production-ready tools, but often don't have the hardware needed to actually see them in action. And so to help towards that, I made what I consider a bit of an absurd experiment, hacking together a minimal demo that most people would be able to run locally on their laptop, and just a way of helping maybe a new contributor or a new developer get hands-on with things like KServe and vLLM in a very simple way. And so to kind of outline what that demo consists of, it basically has the following. It runs a small, lightweight model that can fit on a laptop CPU. It uses Kind, which is Kubernetes in Docker, to create a local Kubernetes cluster just on your laptop. And I'm sure you could try Minikube as well or other options out there. It simply follows the KServe quick start setup on that cluster. Again, like trying to make it as simple as possible for somebody to actually spin up and get something running. And then vLLM ultimately runs under the hood when deploying that model in KServe. And so this is what deploying a model in KServe looks like. So once you have your Kubernetes cluster and you've run the quick start install, which is very straightforward, you actually create a custom resource in KServe known as an inference service. And this is the main interface that KServe uses to manage models and expose the endpoint for actually serving inference requests to that model. You can think of an inference service as like a logical representation of a model. You can see that I specified a model format or type. Well, first at the top, it's the model name, which is just some arbitrary name I give the model. And the model format or type down below indicates which kind of model I want to serve. I didn't mention it before, but KServe is not primarily just for LLM serving. It actually started as a model serving platform for all of the like traditional type of machine learning models there are, right? So KServe also handles models like TensorFlow models or PyTorch models, scikit-learn models, and so on. And so I say that because in this case, the model format is a Hugging Face model, among all of the other ones that it supports. And then below that, I have my runtime arguments here, which point to the model I want to run. I use that Llama 3.21 billion parameter model, which is fairly big, and I think probably the biggest one I could run in this hacked together demo. There are many smaller models. I would probably recommend like a 125 million parameter model if you wanted to scale up to like 1 or 2 models at least. But yeah, that's up to you, and the runtime arguments there are basically just pointing to that model where it'll get pulled. And I also add a backend argument there to explicitly pass that vLLM backend, which is actually the default backend used, but I added it there explicitly just for visual sake. Then below that is the container image Hugging Face server, and this is KServe's runtime image for text generation models. It has many other runtime images as well. Like I mentioned, they support many types of models, but these images basically bundle everything that we need to serve the type of model in question out of the box. So finally, that ... at the bottom is things like resource requests, and that's something that any person working on their laptop, depending on their specifications, would have to work around with and play for those numbers to actually get some type of performance and avoid the pod getting kind of stuck on load. And so here I will pull up, I did a video because I don't trust live demos for myself. I'm kind of cursed. And so it's very simple, straightforward. It's not like very fun to look at, honestly, but again, it's sort of this absurd experiment, and it's aimed at those types of developers who want to just try the thing, right? Like you look at maybe like job applications or things, and they say KServe, and they say vLLM, and all these things, and maybe you don't necessarily work for an enterprise where you're actually using those things in the first place. So how can you actually look at what it feels like? I kind of think of it like maybe paper trading in the stock market or something, where you're just kind of simulating the thing, right? So at the top here, I'm just, oh, not at all, okay. Well, like I said, it's not that fun, but this will make it very interesting to do. Let's see. Yeah, let me do that.
Or you can come down here.
Yeah, I can walk around. No, here, I'll not extend my screen. Nice. Okay. Time to show the demo I've really downplayed as a Frankenstein experiment. But here I'm just creating this inference service, and that's basically kind of what I showed before. You know, things like my runtime arguments are in there, the model I actually want to spin up, and there we see it's created. I'll skip forward here too, but the first thing that happens is a pod spins up, and this pod is KServe's pod, which is now hosting the model. And in that pod, the idea of the inference service is being pointed to. There's a couple of containers. One is the actual thing hosting the model. Another container is the Q proxy, which is how they deal with scheduling the requests and bringing them to that model specifically. And then here, when I do this get ISVC here, oh, I can highlight, that's nice. You could see some information. Clearly, it's not ready. And that's because the pod is actually spinning up. So I'll zoom out a bit here. But here I'm just running, I just want to follow the logs of that pod because I want to show, and again, some developer at home maybe wants to see what actually happens when I'm spinning up some model on this KServe pod. And after about, I think it was like about 30 seconds, some of the vLLM stuff starts happening. And again, like it's not the most interesting thing to look at here at a talk, but the point is that a developer has just spun up a Kubernetes cluster on their laptop, they've installed KServe, and now they've deployed a model, or at least it's in the middle of deploying, using vLLM as a backend. And all of these logs that we're seeing here is not KServe logs, these are the vLLM logs, right? It's initializing that V0 engine. We can see our model that's being served. We can see other things like a bunch of the arguments that we could pass if we wanted to serve a model in a different way, and so on. And then ultimately, once it's ready, it ends up looking like this. We can see like the application startup complete, and the endpoint is ready. And so now we'll do the fun part, which is kind of inferencing, sending a request to the thing. And so in the top right, let's see. Can I zoom in? OK. So in the top right here, I'm just the same way that KServe explains in their docs to copy and paste and port forward the inference service that's being hosted there. That's what I'm doing there. So now it's open for requests from my laptop. Then here at the bottom right, I am running a little script, which is just basically a curl request with some kind of prompt, sending it to the model name that I've chosen, and that's getting sent off. And then in the top left, I'm once again following the logs of that KServe pod, which is hosting that model. And as soon as I send the request, you can see, I think at some point you can see what the prompt was. My prompt is very simple. It's just apples, bananas, oranges, and of course the assumption is that maybe the list could continue. But you see all of the other information, right? You can see there's an ID for a completion request, and if the developer went into the vLLM code, they would see where that completion request, like how this token gets created like that when a prompt actually comes in. Then there are all the sampling parameters that we could play around with, like temperature, to make that model be a bit more wacky or a bit more straightforward and predictable, and all of these other types of things, right? Again, keep thinking of that beginner developer who just wants to see the thing in action, and then once we start seeing that it's actually being processed, we see very unimpressive numbers like 0.2 tokens per second being run. But again, it's entirely on your laptop. You, again, have a Kubernetes cluster with KServe installed. You've deployed a model using vLLM, and you're seeing vLLM work in the background in real time. And then at the bottom here, when we actually see our, when the request is finished, we get our response here, and the text here, this model was pretty good. It said grapes and more, kind of like telling my prompt to stop talking, stop like giving me more fruit. I just want to end the sentence there. And so I think that's a pretty good response. We see information like our prompt tokens, our total tokens, and so on. And yeah, so that's sort of, again, like an end-to-end Kubernetes cluster, KServe installed, deploy a vLLM model, send an inference request on it entirely on your laptop without getting it to blow up on you. And from there, that developer who wants to contribute to this AI space or learn more could go in many directions. They can learn about Kubernetes more. They could try out more things that KServe has, right? Like I mentioned, the model load cache and things like that. They could try to see that in action. Or there's the vLLM route of trying to see what other parameters I could play around with to make that inference faster on my laptop. And so with that, this is I guess I'll pull it up here. So yeah, these are just some resources. The first couple of links are obviously just links to the repositories of these projects. There are Slack channels that you can join if you want to ask questions to the actual developers of those projects. They're both incredibly active. As I mentioned, vLLM has over 1,000 contributors. KServe has hundreds. My contact information, and then at the bottom right, I have a link to a tutorial, which is basically a written version of this talk / the demo I gave at the end, so it's easier to copy and paste. But yeah, if that's something interesting to you or something you think that maybe a friend or somebody newer to the space would be interested in, I think that's a helpful tutorial or guide to get started with. And I'm a lot earlier than I thought I would be, but that's the end of my talk. So thanks for listening, and we'll take some questions. Yeah, of course, let's do it. First, let them clap, yeah.
Can you talk about how this project intersects with the new LLM?
Yeah.
Particularly, you were showing the inference service, which I believe the LLMs are using the inference gateway, which has a different API.
Yeah.
Standardized in Kubernetes gateway. So I wonder if this is like the prior baby from LLM,
yeah.
and the LLMD is the new baby. So
yeah, honestly, basically that. So, I mean, I submitted this talk, months ago, and then since then, there's other solutions for sure. There's also vLLM production stack. There's LLMD, like you mentioned. All of them, I think, are kind of playing for that same space, which is the sort of scaling and infrastructure side of LLMs on Kubernetes. LLMD, I'm not as familiar with, but But the thing is, kind of you touched on it, and I sort of mentioned it before, where KServe was not primarily created for large language model inferencing on Kubernetes, right? It does a lot of other things with a lot of other models, and then only within the last, I don't know, maybe a few months, I think, have they maybe pivoted and created new things to actually support LLMs. You mentioned inference service versus inference gateway, which I guess is LLMs. Or LLMD's version. Yeah, inference service is KServe related. It's not like a Kubernetes concept, right? It's just.
It's not the standards, right? Because it's only
Yeah.
adopted by KServe, while the inference gateway
Yeah.
has been implemented across different projects. So what was
Yeah,
the
and
nature of the inference?
I don't know. I maybe argue that the standards space maybe it's a bit more, I don't know, like contested than that, because KServe, again, with all of the other models that it also supports, like TorchServe, ML server, Triton server, all of these other types of serving runtimes, those projects have all standardized to the inference service way of doing things as well for KServe. So KServe is usually in those conversations when it comes to like the standards of these protocols. But again, I'm not like arguing to or like for one or the other, but yeah, it sounds like both of them are probably pushing towards some kind of standard, which is probably a good thing. But I don't know which one's the real standard yet. Yeah.
With the vLLM, I know you can span multiple GPUs with a single model. Does KServe allow us to span multiple GPUs across multiple nodes? How much control that you have,
I'm not sure. I don't wanna say yes or no because I probably haven't delved into that part of KServe, but I don't know. I don't even want to give you a yes. Yeah. Sorry? Okay. Thank you. There's ongoing work. Yes.
Do you know if KServe can pull from like a private model repository?
Yes. Yeah, definitely.
Like compensation crashes and everything?
Exactly, for sure. And not just that, but also it could be on persistent volume storage. It could be, yeah, like they're very, very varied in where they pull those models from, for sure. Okay, well, I don't know if I'm sorry. That means we get to go get lunch early, right? And be first for the sandwiches, but yeah. Thank you for listening. Thanks a lot.